Okay. Okay, so we are in our PowerPoint notes now. If you can, please open your PowerPoint notes. This is what we discussed so far, all right? There are two ways in which our system can exchange energy with the surroundings. They are heat and work. Remember, heat and work are not energy that the system contains. It's energy that it exchanges with the surroundings, and they are measured as such. Heat is calculated by taking the mass times the specific heat times the temperature change of our system, and that's how we calculate the heat. And work is exchanged by the product of minus the pressure times the change in volume. Remember that we really only observe work being performed when you have an expansion or compression of a gas during the process, okay? Okay, the diagram in the bottom shows you that. And one of the things I believe we've talked about is, by the way, I'm trying to look for my little tools here. See if I can find them. Here they are. Okay, so we talked about work, right, in the previous lecture, but we really haven't talked exactly about, for example, how is heat actually measured? How do we measure heat in a process? All right. So this is the science that is called calorimetry. And that's the topic of our lecture for today. All right. So I'm going to go for a few moments and then I'll come back and check if you have any questions. Feel free to, interrupt, open your audio and interrupt if something is just not working out or anything like that. Okay. Remember, according to conservation of energy, if the only way that a system is exchanging heat, energy with the surrounding is through heat, then you have two components. Heat either put out or absorbed by the system, and heat either put out or absorbed by the surroundings. And because energy has to be conserved, those two have to add to zero, right? So just like we said before, if I look at my system as let's say a circle here, a shaded circle, and I think of the surroundings as everything outside the circumference of that circle, if the system releases heat to the surroundings, we call that process exothermic, and Q is going to have a negative sign. If, on the other hand, the system absorbs heat from the surroundings, we call that process endothermic, and in that case, the sign of Q is going to be positive. Now remember, when I say system, typically in chemistry, we're talking about a process. Let's say, for example, a metal being heated, or let's say a liquid being vaporized, or a chemical reaction happening. That is typically what we mean by a system in chemistry, all right? Now, in order to study this properly, we need to set some parameters. Here are three different scenarios for how we should set up our system. On the left, let's say I have a bottle of water and it's open, and that's an open system because the water vapor that forms as the water vaporizes can escape. And because the container has no insulation properties, the water inside can exchange heat with the surroundings, and we call that an open system, all right? And we would say that in that case, both mass and energy can be exchanged with the surroundings. In the second case, I put a stopper on the bottle. That means that although the water is vaporizing, the total amount of material inside the flask remains the same. However, because there's no insulation, that water can still exchange heat with the surroundings. We call this a closed system, and it allows only for the exchange of energy. The third case is what we call an isolated system. Notice that not only have we closed off the escape of the water vapor outside, but we've also insulated the container so that no longer can energy be exchanged between the inside and the outside of that container. This is what we call an isolated system, and in this case, there is no exchange between our system and our surroundings. This is what we're going to try to set up, all right? This is how we do calorimetry, all right? Okay, so let's move on here. Now, calorimetry is going to be used to determine the heat change of a system. And this is what important, by measuring the heat change of its surroundings. All right. What we're going to do is we're going to set up a isolated system so that essentially everything inside the container contains both the system and the surroundings that we've artificially set up for it. In other words, what we're going to set up is a apparatus or equipment that essentially encloses a, like a micro universe. Now, if we were at a fancy lab or a great place like, Caltech or something like that, this is the type of instrument you would have. This is a digital calorimeter with all the bells and whistles. Now, we are in a community college, so if we were doing an experiment like this, what we would be using is this, a pair of styrofoam cups with a lid and a thermometer. All right, so let me show you how that works. Notice that what we have here is, again, a double styrofoam cup for insulation with a lid. And in the lid, we've punched in a couple of holes, one for a thermometer and one for a stirrer. Now, we probably don't have both of these at the same time. When we do the lab, quote unquote, although we'll do that virtually after spring break, we're only going to have the thermometer in there. Notice that inside the calorimeter, you have water and a sample. In this case, I believe this is just kind of like a piece of metal that we have in there. Now, notice what we've done. We are calling that piece of metal, that sample, our system. And we are calling the water our surroundings. Why? Because by insulating everything inside, we've created essentially a universe in here. The water is the surroundings. The sample is our system. And what we're going to measure is the temperature change that will happen in the water. Now remember, according to the law of conservation of energy, the heat that is exchanged by our sample should be compensated by an equal but opposite sign change in the surroundings, which is the water. Q of the system plus Q of the surroundings equals 0. All right? And that is our calorimetry setup. We've essentially organized a mini universe inside that styrofoam cup. Our sample, in this case a piece of metal, is the system, and the water, whose temperature we measure, is the surroundings. Okay, so what we're going to do is we're going to do this following exercise here. And what I'm going to do is I'm going to switch over here to my makeshift doc cam so we can answer the questions here in order. Hold on a second here. Let me get my notes together. And we're going to come back here to my screen. Okay. Thank you, Alexa, for answering some of the questions. It's great to have Alexa with us. By the way, Alexa's going to be having a SI session later today. So later today, what we're going to do is we are going to let you let Alexa, address you guys so that you can get some details about the session. All right. All righty, guys. We are going to go now to my my makeshift doc cam here. And this is the slide that we were looking at. A 45.2 gram sample of a metal alloy is heated to 100 degrees and then placed in 125.0 grams of water held in a calorimeter at 22.5 degrees Celsius. The final temperature of the water is 29.0 degrees. Assume that heat exchange only occurs between the water and the alloy. In other words, there is no exchange between, let's say, the water and the inside of the calorimeter. Okay, we're going to make that assumption for now. We're going to change that later on in the course. Okay, what is the specific heat of the alloy? Remember that we told you that the specific heat is a property that tells me essentially how much energy does it take to increase the temperature of a substance by 1 degree Celsius. And we said that different substances have different specific heats. We showed you a table with values, but we never told you, how do you find that? Well, this is a typical experiment. So let's go ahead and set up our problem here. Number one, remember, in the calorimeter, the heat exchange of our alloy plus the heat exchange of the water should net out to 0 because of the conservation of energy. What that means is that whatever heat was transacted by this metal alloy has to be the negative of whatever heat was transacted by the water in the calorimeter. So let's see what is the heat change for the water, all right? Remember that we gave you the so-called MCAT formula, right? So this would be the mass of the water times the specific heat of the water times the temperature change of the water, all right? So let's see what those are. The mass of water is given here in the problem. They say it's 125.0 grams. So let's write that in there and make sure you write the units. This is going to be significant. Okay, what is the specific heat of water? Man, they didn't tell us. So at some point, what you'll have to do is, get used to looking things up. Your text should have some appendices in the back or in the inside cover or somewhere that gives you these values. But the specific heat of water is 4.184 joules. That's the unit of energy per gram per degree Celsius. Now we're using joules because that's the unit we typically use in chemistry. Remember that the other unit is the calorie, and if we use calories, this value here would be 1 calorie per gram per degree Celsius because that is the definition of a calorie. All right? Oh. All right. Now, what is the temperature change? Don't forget, it's always final minus initial. Don't get mixed up. There is a sign to it. Okay, it says the final temperature was 29.0 degrees and the water started at 22.5 degrees Celsius. Okay. Now, I'm going to give you a few moments to tackle that calculation. I forgot to get my calculator, so I'm going to go pick it up. Okay, here is my trustworthy calculator. Let's see where would be a good place to put it in. How about over here? Okay, so 29.0 minus 22.5 equals 6.5 degrees. Now, we're not going to change anything yet or round anything, but notice that that number only carries 2 sig figs. So when I multiply that times 4.184 times 125, okay, it's going to give me something like 33,995. I'm sorry, no. Sorry, 3,399.5. And let's see what the units are. Grams will cancel with grams. Degrees Celsius with degrees Celsius. So this number essentially equals to 3,399.5 joules, but because the sig figs were limited by this difference here, we had to round that to 2 sig figs, so that'll be 3,400 joules of energy. All right, that is the energy that the water absorbed. Notice that it's positive, which makes sense because the temperature of the water increased. That means that water must have absorbed heat. Where did the heat come? It came from our alloy. So let me get the calculator out of the way and let's see what the alloy's change was. Well, the heat exchange for the alloy would have been the negative of the heat exchange for the water, which would be then minus 3,400 joules. Now, what I'm interested in is, Well, what is this heat of this alloy? Well, it would be the mass of the alloy times the specific heat of that alloy times the temperature change of the alloy, not of the water, of the alloy. All right? So let me move this up a little bit so I have some room. So what we're going to do is solve for our unknown, which is the specific heat of the alloy. So let's see what that would be. Specific heat of the alloy would be minus 3,400 joules divided by the mass of the alloy, which we have up here in our problem, was given to us as, 45.2 grams. And now let's look at the temperature change for the alloy. This is what's important. Final minus initial. In this case, we have to make the assumption that when the water arrived at 29.0 degrees, that is the same temperature to which the alloy arrived. Remember that example I gave you, the two tanks next to each other at different levels of water, and then you open a little valve in between, and the water essentially levels off. Similarly here, the idea is the metal was starting at a higher temperature than the water, so there was thermal energy transferred from the metal into the water until they both arrived at 29.0 degrees. So that's the final temperature of our metal. What temperature did the metal start at? Well, it tells us here that it started at 100 degrees. I'm going to put that in there. And of course, make sure that you respect the sig figs. 10.0 degrees Celsius. Okay. And again, let me close the parenthesis here. And again, I am going to let you guys come in and do those calculations by yourself. I'm not going to do it. Okay. I'm going to just show you what the final result is. This number here is going to be probably about 3 sig figs. But remember that our input value here only had 2 sig figs anyway. So when you do the calculations, this is going to come up to be 1.1. Look at the units, joules per gram per degree Celsius. Okay, so that is how we solve this problem. Okay, don't forget, at the end of the session, besides the recording, you'll be able to have access to scans of these pages that I write, okay? Yes, I do that for you guys. Okay, let's come back here then. And let's go back to our PowerPoint. Okay, so that was the answer there. Okay, here we go. So sometimes this concept of specific heat or specific heat capacity, sometimes what it does is it's a little, it's one of those terms that has kind of evolved over the years. And so many times, depending on what you're reading, they're going to give different meanings to it. For example, sometimes heat capacity refers to a calibration of the specific calorimeter that you're using. And so we use just simply here capital C to indicate a value that is going to be simply in joules per degree Celsius. In other words, it's not going to be based on mass. Sometimes the concept of heat capacity is more of a general term that talks about a substance's, intrinsic ability to absorb heat. So I can say, for example, like we did an example in the second lecture, the one that you're supposed to do by yourselves, water has a greater heat capacity than sand, right? It's kind of like a qualitative thing. But of course, if we want to get into numbers, we can then say, well, we're talking here then for about this specific heat, which is kind of like what we're using most of the time in our presentations here, the joules per gram per degree Celsius. Every now and then, and again, because of the different applications we have, we would prefer to talk about the molar heat capacity. So instead of being the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius, this is for 1 mole of the substance, and it has units of joules per mole per degree Celsius. Okay, so be aware of that.